Hello, Math 1. So today we're going to talk about the applications of exponential functions, right? We're going to break it down with two examples, and then we're going to basically jump to section 10.5 and do a couple of more examples there. So where we're going to start is on page 23, okay? And the first type of application problem we're going to talk about relates to exponential growth. So we're going to look at the exponential growth model a little differently. All of the exponential growth models we've looked at right now have been in the form y equals a times b to the x, but we've also called b the r, right, for common ratio to the x power. But now we're going to change it up a little bit, right, where we're going to see this y equals a times 1 plus r all to the t, where a is our initial amount, okay? Then r, right, is what we call the growth rate. Time, right, the t up here is always time. And then finally, when we take the 1 and the r and we add them together, it gives us what we call the growth factor, okay? So what does that all mean? So we're gonna talk about this through an example. And I'm going to shrink this a little bit. And the first example says, Jack bought a house for $120,000 in 1990. Houses in the neighborhood have appreciated approximately 4% per year. Let X represent the year 1990. How much will it be worth in 1993? So what this is in 1990, that's year zero, we have this house and the value of that house is $120,000, okay? So then you own that house, right? And it goes up in value and it increases by 4% per year. So what we're going to do is we're going to do the long way and then we're going to break it down to the shortcut. So what we have here is in year one, right? Anytime you calculate with percents, you have to know that you have to convert a percent to a decimal, and you can either move the decimal 2 places to the left, or you could basically take the percent divided by 100. So when we're looking at 4% here, 4% as a decimal, if I take 4, I divide it by 100, the decimal would be 0.04. Okay, so anytime we calculate with that, we have to convert it to a decimal. So after year one, what do we have here? Well, what I'm going to do here is I'm going to find how much it goes up in value. Since it's going up 4% per year, we're going to take 0.04, multiply it by the value of 120,000. So I'm going to take 0.04 times 120,000, and you get $4,800. So that's how much it went up from the beginning to the end of the first year. So now, what is the value of the house after the first year? Well, now I'm going to take the 120,000, I'm going to add the amount it went up of 4,800, and now we know if I add 120,000, it's going to be 124,800. But now when you go to the second year, right, it goes up another 4%. What you have to understand is the next round, right, it's going to go up 4% from the current value, which is 124,800. So for the second year, we're going to take 0.04. We're not going to multiply it by 120,000. We're going to multiply it by 124,800. When I do that, I'm going to go to my calculator, times 0.04. So the amount it goes up now is $4,992. So I'm going to take that and add it. I'm going to take the 124,800. I'm going to add 4,992. And I get $129,792 is the new value. So now, after the third year, you have to understand that now the value is going to go up 4% from this value. So we're going to take 0.04, We're going to multiply it by that new amount. So this times 0.04 will give you $5,191.68. So now the value after 3 years would be the $129,792 plus the $5,191.68. So plus the $129,792 gives you a new total value of, after 3 years, $134,983.68. That would be the value of the house, right, if it continued to increase 4% per year. All right, this is what we call compounding, okay? Now, here's the thing, though, right? If I asked you how much this house would be in, say, 2020, would you want to continue this process over and over and over? No, right? So is there a quicker way that we can get these answers? Well, anytime I want to add a percent of something, right, what I do is I say 100% is equal to 1. So when I look at it, the value of this house is going to be 104% of the previous amount. So if I took 104% and divided that by 100, it would give me 1.04. And notice here now, if I take the 120,000 and I multiply it by 1.04, 120,000, oh, why is this frozen? 120,000 times 1.04. Notice how it gives you that 124,800. Isn't that the same amount I got when I found the 4% and added it? So if I took this and multiplied it by 1.04 again, I'd get the 129,792. And again, if I multiplied that by 1.04, I would get the 134,983.68. So the easiest way to add a percent to an amount is to go 100% of the amount plus the percent increase. So 104% is equivalent to 1.04. So now, can we come up with an exponential function that models this? Well, here's the thing. If I look at this and I say y equals, you have to know that A is your initial amount. And our initial amount here is 120,000. Our growth rate is 4% or 0.04. So if we go up to the top and we take this model, we know A and we know R. So now I'm going to fill that in, and I'm going to say y equals A, which is 120,000, times 1 plus 0.04. And then instead of using t, I'm going to use x to the x power. Now that also translates to 120,000 times 1.04 to the x power. This is the function we want to focus on. And the nice part about that function is, here's what I want you to see. If I want to figure out what the price of this would be, right? Y equals 120,000 times 1.04. In year 3, or in this is year 1993, if I raise that to the third power, 120, if I go to my calculator over here, 120,000 times 1.04 to, 120,000, open parentheses, 1.04, close parentheses, to the third power. Look what it gives me. It gives me 134,983.68. So if I wanted to figure out what the price would be in the year 2000. That would be x is 10, so 120,000 times 1.04 to the 10th power, 12,000, open parentheses, 1.04 to the x power, we're replacing that with 10. That house would have a value of $177,629.31 after 10 years. So coming up with this function model is critical. So now what about exponential decay, right? When I look at exponential decay, it's no different. You still have your initial amount, right? Then R is still your rate, in this case, it's not going to be growth rate, it's going to be decay rate, meaning it's going to go down a certain amount. T is still time, but now the 1 minus R, if you notice here, the difference between it is we're subtracting R, it's going to be the decay factor. So when we use an example to come up with this, notice what you see. Bob bought a used car for $12,000 in the year 2000. It depreciates at a rate of 15% per year. All right, so how much will the car be worth in 2003? So year 0 is basically the year 2000. Year 1 is the year 2001, 2002, and so on. So the value in 2000 we know is $12,000. But the next year, it's going to be worth 15% less. So if I convert 15% to a decimal, 15 divided by 100 would give me 0.15. So if I take 0.15, multiply it by $12,000, 0.15 times 0.15 times 12,000, you get 1,800. So now, that's how much it goes down. So to figure out the new price or the new value, 12,000 minus 1,800, so 12,000 minus 1,800, you would get 10,200. So the value after 1 year of that car is $10,200. So now, to figure out the value after 2 years, I'm going to duplicate the process. 0.15 times the new value is 10,200. So if I take that 10,200, multiply it by 0.15, you would get $1,530. So that's how much it's going to go down this year. So now the new value, 10,200 minus the 1,530, the new value of that car would be $8,670. Now I can duplicate the process for year 3, right? I could take 0.15, multiply it by 8670, right? So times 0.15, it gives you 1,300.5, and then 8670 minus that amount, so minus 8670 would give you a value for that car of $7,369.50. So that's how much a car would be worth in 2003. The thing here, though, that differs between exponential growth and decay is how can I get straight to these values, right, without having to multiply by the percent and then subtract? Well, here's the thing. When it's going down 15% per year, right, what percent of the value is it holding? Well, if I take 100% and subtract the 15% is going down, that means that car is holding 85% of its value every year. So how do I convert 85% to a decimal? I divide it by 100, and it's 0.85. So That is the same as if I took 1 minus the rate, so 1 minus 0.15. If I go to my calculator here, 1 minus 0.15, notice what you get, 0.85. So when we go to the formula up here, that 1 minus r, this is what we're doing here. This is basically what we're trying to figure out. And if you look here, okay, if I take 0.85 and multiply it by the original price, 0.85 times 12,000, you get $10,200. Doesn't that match up with the value after 1 year? Now, if I take that, multiply it again by 0.85, you get 8,670. So 0.85 times 10,200. And then if I wanted to, after year 3, 0.85 times the 8670. If I multiply that again by 0.85, notice what you get, $7,369.50, which matches up there. So how can we take and write this exponential function rule to model the depreciation of the car after X number of years? Well, we know A is 12,000. That's our initial amount. Our rate of depreciation is 15%. And if we convert that to a decimal, it's 0.15. So we start with Y equals 12,000 times 1 minus 0.15 to the X power. But now I'm going to take that, right, and simplify the inside part. So the function that models this would be Y equals 12,000 times 0.85 to the X. And if I wanted to in C, determine the value of the car after 7 years, well, I'm going to let X equal 7, so Y equals 12,000 times 0.85 to the 7th power. And notice what we get here, 12,000 times 0.85 to the 7th power. And right away, the value of that car after 7 years would be $3,846.93. So this is going to lead us into the examples that follow, right? So we need to make sure we have this done in order to, do the notes the next day. All right. So right now I want you guys to make sure you have the 10-1, the 10-2, and the 10-3 homework done, and make sure we're checking our answers. All right. Enjoy your afternoon.